So we want to finish up the section. So the guys are 2 lessons, 2.4, 2.4, and 2.5. These are the last 2 lessons in our exponential unit. So this unit had 2 quizzes. Okay. So let's take a look at a couple of things. So in our exponential models, we started out with an exponential model looking like this. The variable y always represented what to us? Yeah, y always represented a future value. Dogs, cats, people, money. There were different formulas, okay? The value a always represented what? The value a always in each of our formulas represented what? Not future, current, initial value, okay? More appropriate to say initial value. Now, if there was a question on the test where, like, we have a model of population. What's the current population? It's always just copying down what this number is, okay? There was one model on your test about population in Atlanta. It said in 1980 it was 5. The model was y equal 5.3 times something. That's your initial value. Okay, this number in front of the exponential is always the initial value, because if x is 0, that means that b to the 0 is 1. You get whatever that value a is. In our case, b always represented, and we called it a growth or a decay factor, and that's what we're going to be spending more time on today. A growth or decay factor. And x in all of our models represented what? Time, okay? So everything we did, all of our models look like this. Then we moved into a couple of very specific models for interest. This is our compound interest formula, okay? What does A represent? Yeah, it means it's the future. It's the future value. P always represented what? Yeah, the initial or present value. So the present or initial value. That's the amount of money you put in the bank. A is the amount of money you can take out years later. R always, in this formula, represents what? Yeah, it's the interest rate and you have to remember how to convert percent to decimal, okay? The problem might say 10%, but you know that's 0.1 in the formula. N always represents what in this formula? The number of what? We were quizzed over this, I think, yesterday. Is that right? Or the day before? Yesterday. What? The number of times it's compounded per year. So the number of compounding periods per year. I didn't mean for it to be a trick question, but it was to some people. If interest is compounded yearly, how many times a year does that mean? What is it? 1. Okay, so n was 1. If n is if the interest is compounded monthly, n is 12. Okay, you've got that. T always represents what in our models? It's time. Okay, this was. How do you know to use this formula when you're reading a word problem? It will say compounded, and the next word will be something like what? Daily, weekly, monthly, yearly, hourly, whatever. It will be a discrete amount of time, okay? There's another formula called compound interest. What is your clue to use this formula? Continuous. You'll see the word compounded, and you'll see the word continuous or continuously. Here, the same thing. A is our future value. P is our initial value. And E is our natural what? How about natural exponent? Okay. E is a natural exponent. R is our interest rate. Okay. Same thing. And T is time. Okay. So this was an easier formula to use because you don't have the compounding periods. Okay. Now, what we want to do, we want to take a look at this general form of the model once more. There was a problem on your test that said, is this exponential decay or exponential growth? What is your clue to that? If you have something like y is equal to 26, 1.11 to the t, okay, is that growth or decay? That is growth. This is exponential growth because that word means because the number that I'm raising to the exponent is greater than 1. So think of it, just pick a number like 2. You're doubling every time, so that is growth, okay? Exponential k would be something like this. Y is equal to 26.7 to the t. That's exponential k because I'm taking 0.7 times 0.7, so it's fraction times fraction times fraction. This is exponential decay. So it all has to do with that number that you're raising the exponent to. If it's greater than 1, then you have exponential growth. If it's between 0 and 1, a fraction between 0 and 1, then you have exponential decay. Now, we write these formulas in a slightly different way, but you can see similarities here. So we're going to write a specific formula for exponential growth, a specific formula for exponential decay. Both of these formulas will be written just like this on your quiz, okay? Someone tell me, what do you think y is? Not a trick question, you should know. What is y? Someone. It is the future value, okay? It hasn't changed. So y is the future value. What is a? Yeah, it is the initial value. What do you think r is? It's the rate, and in this case, it's going to be the rate of increase, okay? So I've written this formula 1 plus r, so something is growing in this case, okay? And then 1 plus r, this is going to be my growth factor. Another way of saying this one right here, this is my growth rate. This number r is always in, that is always in percent, okay? And then in this model, what is x? Time, okay? If I look at writing the formula like this, 1 minus r, everything is the same. So this is also, this is my, most everything is the same. This is my future value. This is my initial value. And instead of r being my growth rate, what do you think r is here? It's decay rate or decrease rate. So this is my decay rate. So it's the rate of decay or decrease. And then 1 minus r, instead of being my growth factor, is my what? It's going to be my decay factor. And what is x in this model? It is what? Time. Okay, it is, the exponent is always time in every model that we have. Okay, so all we're doing is we're writing this model as a number that's bigger than 1 or a number that's smaller than 1. Okay, and when I look at this, r is how much it increases. That's its increase rate. 1 plus r is the increase or growth factor. Okay, so you got two things to worry about. The growth rate. When I say rate, I always mean percent. Okay, when I say factor, I'm looking at a number. Okay, so let's look at one for example. And some of this you should know. Now, you should look at that without even knowing what that represents or what it models. What is the initial value there? 1200. The initial value is 1200. There's no computation that goes along there. Whatever this models, the initial value is 1200. Okay. Now, do you think this is growing or decaying? It is decaying. Why is it decaying? The number inside parentheses, is it bigger than 1 or smaller than 1? It is smaller than 1. That makes it exponential decay. Okay? Now, the growth or decay, in this case, it's a decay rate. I look at this, so my formula was y equal a 1 minus r to the x. Okay. So this is telling me what my decay rate is. Okay. So my decay rate is 0.0075, but it's always in percentage. How do I convert that to percentage? What is it? 0.75%. Okay, so 0.75%. That is my decay rate for this model. Okay? Everyone see where that comes from. Now, the growth or decay factor is a number. It's just whatever that number is inside the parentheses. I would rely on my calculator. So what is 1 minus 0.0075? 0.9925. So 1 minus 0.0075. So this is 0.9925. Okay. So this is probably as hard as these problems get, to know the decay rate and the decay factor. Okay. So the decay rate is a percentage. This model is always decreasing by 0.75% per year. This is my decay factor. Okay, one of these numbers is percent, one is just a decimal number. Let's look at the next one. 23,200 times 0.64 to the t. What is the initial value? Yeah, 23,200. You should really never miss this from now on. Okay, it's as hard as copying the number that you see in front of the exponent into the box. Okay, is this growth or decay? This is decay because that number inside the parentheses is a number that's smaller than 1. Okay. Now, what is the growth or decay rate? Or which is easier to figure out here, the factor or the rate? Okay, the rate is a percentage. Yeah, the factor is already there. The factor is what, Maddie? 0.64. It's that number inside the parentheses, okay? But to find the decay, so this is my decay factor. To find my decay rate, I need to figure out 0.64 is equal to 1 minus some number, okay? I need to figure out what that number is. How do I figure this out? Come on, guys. How do you figure out what R is here? Pardon me? Well, not move the decimal. I'm solving for R. What do I do here? Come on, guys. This is not that hard. I what? Yeah, I could subtract 1 from both sides. I can move the R to the... Anyway, I've got to figure out. So if I look at this, this is going to be R. If I move the R to the other side, R is equal to 1 minus 0.64. Okay. So I'll put that in my calculator. Just use your calculator. It's there, so you don't make the arithmetic mistakes. 1 minus 0.64 is 0.36. So that tells me that 0.36, or how many percent is that? Yeah, so this is 36% is my decay rate. Okay. So when I ask for rate, I'm looking at a percentage. Okay. So all I did was, all of these formulas are either 1 plus R or 1 minus R. So if I look at 0.64, that's 1 minus what? That's 1 minus 0.36. So this is a 36% decrease or decay. Look at the next one. The initial value is what? 200, okay? Is this growth or decay? This is growth because the number inside the parentheses is what? greater than 1. So this is growth. What is the growth factor? The growth factor is the number inside parentheses. What is it? 1.22. Okay. To find the growth or decay rate, I need to write 1.22 is equal to 1 plus some number. What number is that? What do I add to 1 to get 1.22? 0.22. So how do I write that as percentage? That is 22%. Okay. So that's 22% growth. Okay, are you getting the handle of that? Okay, let's take a look at a word problem that has this here. And like I said, you will be given these two formulas. Okay. The population of College Park in 2014 was 14,598. If the population is growing at a yearly rate of 3.4%, write an exponential model for the population P in terms of years T. Okay? So I want a population formula. So the population in terms of years. So the population P in terms of years. Okay? I want to write this as an exponential model. What is my initial population? 14,598. Okay. And this is growing or decaying? Growing. So I'm going to write, which of these formulas will I use? Top or bottom? Bottom formula. So it's going to be 1 plus, how much is it growing? 3.4%. How do I write 3.4%? 0.034 times T. Okay, so what is T in this case? T is what? The years. What kind of years? T represents in this model years what? Years since a certain time. Years since 2014. Okay? Because 2014 is when my model starts. Okay? And then P, that is the population. Okay? What is the growth factor? The growth factor is what? Is a number. 1 plus what? 0.04. So it's 1.034. Okay? The growth rate is 3.4%. The growth factor, the number inside the parentheses that I'm raised to an exponent, is 1.034. How do I find out what the population will be in the year 2020? I need to substitute T is equal to what? T is equal to, is a number, am I not hearing it? 6. Why T is 6? T is the number of years since when? 2014. How many years after 2014 will be 2020? 6. Okay, so all I do is just plug this into the formula. So 14,598 times 1.034 to the 6. And I will go to my calculator. 14,598 times 1.034 raised to the 6 is 17,840.9. So about how many people is that? If it were people, I wouldn't do like, it's not 90 cents worth of people over there on that decimal. So 17,841. So this is about 17,841 people in the year 2020. Okay. So just plugging into the exponential formula that we have, the two key things here are this growth rate, growth factor, decay rate, decay factor. Okay. Now, you really need to pay attention here because life's going to get a little bit simpler for you. In what year? Yes. Okay. In what year? Just by reading those three words, they're asking me about what? Time. Time is always my exponent. How do we solve for an exponent? We use logs, okay? What I will just sort of, let me take a little bit of an aside here. When you, if you ever get to calculus, you don't have to take notes on this, but in calculus, you spend about the first 2 months doing stuff like this, okay? I know it looks complicated, but they give you something like, they give you x squared. They make you do all of this stuff, and your answer is 2x, okay? You do that for about a month or two, and then they come in one day and say, you know what you do? You take this x squared, and all you have to do is just move that 2 in front, and the answer is 2x. It has a lot of different meanings. But anyway, you do all this work, you know, it's sweat on your brow, and you're making algebra mistakes, and then you come in one day, and they give you a rule of how to do it, and they say, well, the derivative of x cubed, that's just going to be 3x squared. You move that in front. So they do these things like this. Okay, so it's one of these days you wake up and like, I've been doing that work. Well, this is sort of that day for you. If you will look at what we do here. In what year would the population reach 30,000? Now what follows are some screenshots about how to do this graphically in your calculator. I'm going to bypass that and just give you a function on your calculator that allows you to solve for the variable. Okay, so if I were to write this out, when would the population reach 30,000? What would I write out? I would write 30,000 equal what? No, yet. Just write out, it's 14,598 times what? 1.034 to the t. That's what I'm trying to solve for t, okay? So what you can do, I'm not going to do the graphical part, so you can skip these screenshots, but this part you do need to pay attention. You can come on your calculator, menu, and then 3, 1. You'll get a solve command. It might be in solve on your calculator. Menu 3, 1. And I'm just going to type that equation we just saw. 30,000 equal 14,598 times 1.034 raised to the t power. Okay, so that is my equation. And then the next thing you have to do, very important, you just put comma and then t. Okay, what this means is solve this equation, 30,000 equal 14,598, 1.034 to the t, solve it for t. Okay, you hit return and you get t is 21.54. Okay, so what you would do here, it's the menu 3, 1. You're going to get the insolve command. And so the syntax is going to be insolve 30,000 equal 14,598 times 1.034 to the t, and then very important, you have to put that comma t at the end. That gives you the value of t. In this case, t is 21.5. So we find that t equals 21.5. What was the question? In what? In what year? So I need to add this to what value? My model started in what year? 2014. If I add 21.5, that is 2035. What year is that? It's the year 2035. So it's the year. Now what did we not use to solve this? Logarithms, okay, which is what you did on the previous problem. You would have had to take the log base 1034. Now you can still do that, okay? I contend that this is an easier way of doing it, okay? So rely on the calculator skill. So anytime you're solving for t, solving for the variable that is your exponent, you can use menu 3.1 to solve that automatically, and you do not have to use the logarithm, okay? Everyone okay with that? So all you'll need to skip, like I said, I didn't want to give you two methods. The graphical method is a little bit harder. So let's just skip this graphical method, and let's just come down to the next problem. So you can, if you just want to make a mark that you're not doing the, you can study that if you want. You can still use logs, but this is probably the easiest thing to do. Let's look at the next one. On her 18th birthday, Anna inherited land that was purchased for $30,000 in 1960. This particular piece of land has increased in value approximately 4% per year. Write an exponential model for the present value of the land as a function of time. Okay, so they want me to have something of the value of the land, so I'm going to say the value of the land as a function of time. Okay, so V is going to be the value of the land. T is going to be time in what? Time in what units? Years, okay? There's nothing but years mentioned in my problem. So the time in years, okay? The next number that always goes in the exponential model is my initial value. What is the initial value for this problem? $30,000. This land was purchased for $30,000, okay? Is the value of this land increasing or decreasing? It is increasing by how much? By 4% per year. How do I write 4%? Like that, okay. And then T is the year. And so this is years. It's time in years, but there's one little caveat. Time in years, and then what goes after that? What are you getting from this? Is it any year? Do I plug in the year 2000? What is it? It's time in years with one caveat that you get from reading the problem. Pardon me? After 1960. So it's a time in years since 1960, okay? So this model starts in 1960 as if for this particular model, 1960 is time 0. That's my initial value, okay? So this is the model that I'm using. V is the value of the land. T is the time in years since 1960, okay? And you can see that it's growing at 4%. That's 1.04. So what is the growth factor? The growth factor is 1.04. What's the growth rate? 4%. Okay, so in this case, just keep in mind that the growth factor, it's that number inside the parentheses, 1.04. The growth rate is always a percent. That is 4%. Okay, so this is the model for an initial investment of $30,000 growing at 4% per year, where the years are since 1960. Now it's going to probably ask me a few questions. How much is the land worth now? Okay, so how do I figure out what year that is? What's the current year? This is 2019. I need to figure out how long ago was what? 1960. That's going to be 59 years. Okay, so 59 years ago, or 59 years in the future is 2020. So I need to substitute T is equal to 59 into that equation. So here I'm going to get that the value of the land is 30,000. And what was it? 1.04 to the 59th power. And that's not 3,000, it's 30,000. So 30,000 times 1.04 to the 59 power. I will go to my calculator. 30,000 times 1.04 raised to the 59th is 303,451. So it's worth 303,451. That's the value of the land in 2019. How much was the land worth in 1970? What would T be in 1970? T is equal to 10. It's 10 years since 1960. So do the same calculation. It's 30,000 and then 1.04 to the 10th power. So I'll just do the same thing on my calculator. I'll cheat here and just raise it to the 10th power, and I get 44,407.30. So it's 44 and 407.30. That's the value of the land in 1970. Okay, now the next one. How much time? That is solving for which kind of variable? My exponent. I can use logarithms or I can use the solve command. Which would be your preference? The solve command. Okay, so I will do, this is where I do the menu. Not sure why that happens. I'll use menu 3.1 on my calculator. Okay, so what I need to do is I need to say menu 3.1, and just before I get there, let me set up what is the equation that I need to solve. The 100,000 is my what? It's my what value? My future value. Okay, V. So I need to look at the equation. When does 100,000 equal 30,000 times 1.04 to the T? I'm solving that equation for T. So all you have to do in your calculator is just write that in. When does 100,000 equal 30,000 times 1.04 raised to the T? Okay. And then I need to solve that equation for what variable? T. So you write comma T. If you happen to pick X, you would write comma X there. You're telling the solve command which of these things is my variable. You hit return and you get 30.70. Okay. So this happens in 30.70 years. Okay. Now the question here, how much time did it take for the land to get to 100,000? This is the appropriate answer. It took 30.7 years. Okay. If the question had been in what year, how does that change? This is what year? Come on, guys. What is this year? 30 years. It's what? 30 years from 1960 is 1990. Okay. So in what year would the answer would have been 1990? It says, oh, that's the next question. Sorry. In what year? That is 1990, because it's 1960 plus 30.7. That's 1990.7. So that is the year 1990. Okay. So all of the problems in this section, they're exponential. The thing that's easier is you can now solve them without logarithms. You got to be very comfortable knowing that command, menu 3.1. It's either going to be solve or insolve, depending on your calculator. And that will allow you to solve for the exponent. Okay, so you don't have to worry about taking the log of both sides now. Let's look at another example. During the economic crisis of 2008, Atlanta home prices began to decrease by an average of 18% annually. Write an exponential model for the value depreciation of a $500,000 house. Okay, so let's just say that the value as a function of time Okay, what's the initial value of the house that I'm trying to model? 500,000. So I've got a house that is initially worth 500,000. Is it increasing or decreasing? It's decreasing in value. So I'm going to write it as 1 minus, what's the decrease rate? It's 0.18. So 1 minus 0.18 to the t. Okay, and what does t represent in this problem? Years what? Yeah, years since 2008. And V is equal to my value in dollars. Okay. So according to this model, and here I can simplify this, 1 minus 0.18, or I could leave it like that. Let's just figure out. So 1 minus 0.18 is what, 0.82. So I could rewrite this as V of t equal 500,000 0.82 to the t. You don't have to do this on your calculator. Either one of them, you can plug in either one. You're going to be fine. Okay, it doesn't really matter. What is the decay factor? It's what? You should be able to look at one of these formulas and tell me. Yeah, the decay factor is 0.82. What is the decay rate? It's 18%. Okay. Okay. The decay rate is always percent. So these houses are going down in 18% per year. The decay factor is that number inside the parentheses, 0.82. How much was this house worth in the year 2012? So what would T be in 2012? T is equal to what? 4. So 2012 is 4 years after 2008. So what do I do with this? Yeah, I just plug the 4 in for T. So V is going to be equal to 500,000 and then 0.82 to the 4th power. So 500,000 times 0.82 raised to the 4th power is 226,061. So 226, what did I say? 061. Was that a good investment? A $500,000 house that 4 years later is worth 226. Yeah. So, I mean, think about that. This was a real number in 2008. But the thing is, this model, do you think that model is still in play? Are houses still going down by 18% per year? Do you think yes or no? No, the economy is better. So this was a short-lived. So this model really had a short shelf life for how long? You wouldn't expect to use this model and say, what would the house be like 50 years from now? That this model, this data was too rapid, too time constrained. How many years? I'm solving for what variable now? Time, which is my exponent. I can use logarithms or my calculator. What are you going to use? Calculator, okay? So what is the equation that I need to solve here? Let's set up an equation. 400,000 equals what? 500,000 and then 0.82 to the t. And I need to solve that for which variable? T. So I would just go to my calculator and it is menu 3, 1. I need to solve 400,000 equal 500,000 times 0.82 raised to the t, and then what goes next? Comma t. Okay, solve this equation for t, and you get t is equal to 1.12. So it took 1.12 years That's how much time it took for the house to go from 500,000 to 400,000. Now, if the question had been in what year is this? This is the year what? How are you getting 2020? What year is this? Come on, guys. Where did the model start out? 2008. 1.12 years from 2008 is what year? 2009. Okay? You guys got to put your hats on to think about this. Okay? And you should be good. So, guys, you will be given both of these formulas. There's really not a lot to memorize. It's just, you know, this tells you that you're increasing by a rate. This tells you you're decreasing by a rate. Okay? And on the TI Inspire, we're not using the graphical method. We're just going to use the solve command. So menu 3.1, and that is the insolve command. So you just need to know how to input an equation in that command, and then comma t or comma x, whatever your variable is, in order to solve it. Now, don't overlook the stuff that is pretty straightforward up front. You don't want to miss points on, you know, what's the initial value? I mean, there were people who missed this on the test. What are the initial values of these three things? 24, 37, 19. Okay, not a lot of thought there, not a lot of computation. Don't miss the initial value. Okay, is this one growth or decay? That's growth. This is what? Decay. This is what? Decay. And then be able to figure out the growth or decay rate, which is a percentage, and the growth or decay factor. Okay, so you don't want to miss points on that. And then from there, you'll just see models of things that you need to figure out. So write an equation of a model that says population at 20,000 that goes up by 3.4% per year. A $50,000 car that depreciates 9.8% yearly. A $100,000 investment that doubles every year. What does it mean for an investment to double? What percent is that? So if I start with $100, what would it mean for it to double? It would be $200. So that means my increase, if I started with 100, how much was my increase? It was 100. So 100 is what percent of 100? Come on, guys. 100%. It increases by 100%. So this is 100% increase. Okay. Okay. So you can figure that one out in the formula. And then I think you've got other things in the homework from there. Okay. So go ahead and spend some time on this. I will see you again tomorrow. Unfortunate thing about the way the cycle works with your class, you get today and tomorrow are the two lessons. That's it. Don't see you on Monday. Is that right? Yeah, don't see you Monday. I think the quiz is on Wednesday then for you guys. If I don't see you Monday, then no, sorry. We review on Tuesday. Pardon me? It's an X day. It's weird. Sorry about that. Okay, so here it is. So I see you on Thursday, Friday. Let me pause this.